So this question says, consider the box moves to the right at a constant velocity, which that is a key idea for us. Basically what that tells us is that the net force must be 0. So it has 4 forces acting: friction, its weight, normal force, as well as a pulling force, which is at an angle to the horizontal as shown. Which of the following options must be true in terms of the relationship of those forces? So what we can do is we can look at Newton's laws, and if we draw our net force equations, understand what is happening. When we're looking at our pull force, we're going to break this into its x component as well as its y component here. So then what we simply need to do is draw our force, or sum of our forces in the x and the sum of the forces in the y, and take a look. So we're going to have our x component of our pull force minus our frictional force equals mass times acceleration in the x direction. We know because it's at a net force of 0 that this acceleration is going to be 0. And so what we can see is that our component of our pull force, is going to equal our frictional force. In the y direction then, what we have is we have our normal force plus our force of our pull in the y component minus our weight is going to equal mass times acceleration in the y direction. Our acceleration in the y direction is also going to be 0. And so what we have is we have r plus our force in the y is going to equal our weight. So these are two things that we can look at when we're trying to compare these forces. Now, if we look at our right answer then, F, which is our pull force, is going to be greater than friction. Right? If a component of our pull force is equal to friction, then because we have a right triangle here, the hypotenuse we know must be greater than the individual parts. And so if x equals our frictional force, then our pull force must be greater than friction, even though our net force still is 0. And we know that our normal force must be less than weight, right? If our weight equals our normal force plus the y component of our pull force, well, then this normal force must be smaller than our weight. Looking at this question, it says a cruise ship is sailing in the Caribbean at a constant velocity. And right away, we know when it says constant velocity that my net force, again, needs to equal 0. Its weight is 5 times 10 to the 6 newtons. A resistive force of 2 times 10 to the 6 newtons acts on the ship. What is the magnitude of the net force acting on the ship? No math, just a simple concept of Newton's first law. An object in motion will stay at a constant velocity as long as the net force is 0. So our final answer can be 0. Our next question says, a book is resting on a table. There's a normal force from the table on the book. According to Newton's third law, there must be a reaction to this force. What is that reaction? So if we think about our table with our book resting on the table, so here's our book. The forces on the book are going to be the force of gravity, or the object's weight, as well as our normal force. Let's actually do this in a different color. Our normal force is going to be up, and we'll designate that with an R or Fn. It really doesn't matter. Now, let's look at the reaction pairs that go with these two forces. So the first one is the weight, okay? And so the idea is that the Earth is pulling down on this book, and that's what's causing its weight. Well, in the same sense, the book is pulling up on the Earth. So if this is the Earth right here, this is our pair. Earth pulls down on the book, book pulls up on Earth. Again, we simply change the directions and switch the place in the sentence where the nouns are found. For my table, it's a little wobbly now, but my table pushes up on the book. The reaction to that would be the book pushing down on the table. And those two forces would be equal in size, opposite direction. So if we're looking, there must be a reaction to this force. It is the book pushing down. So the book pushes down on table. It's not the weight. The most common misconception would say it's the weight. They're equal in size, opposite direction, but again, they're acting on the same object, which doesn't work in Newton's third law. A box of mass M is being pulled to the right of a rough surface by a force of F, acting at an angle to the horizontal. The box does not lift off the ground. Between the box and the ground, there's a frictional force. Given the box accelerates to the right, find an expression for the acceleration of the box. Okay, so this, I love this question. It basically has us solve for this without any numbers, right? So we have a box which is accelerating to the right. So that's the direction of our net force. That's the direction of our acceleration. We're going to say that's in the positive direction. So what are the forces then acting on the box? We have some pull force, which they call F. We have a frictional force acting backwards. We're going to have the force of gravity, or the weight of the object. And then we're also going to have some resistive force here. And what we're trying to solve for is the acceleration to the right. So if we do our sum of forces in the x direction, we're going to have this pull force, which is going to be broken into its x and y component. So that's the x component, that's the y component, and they say at some angle theta. But they don't give us that value, and that's okay. What we know is that this in the x direction, we simply have the force pull in the x minus my force of friction equals mass times acceleration in the x direction. And really, this is what we are trying to solve for. Okay, so let's look at that. Now, how could we first solve for f of x? Well, from our triangle, if this is f, and this is x and y, and we know that is theta, I'm going to look at this and say, okay, this is the adjacent side, this is my hypotenuse, so I'm going to use cosine. So the cosine of theta is going to equal my adjacent, which is fx, over my pull force, which is f. Solving for fx, then I'm going to multiply each side by simply the force, pull, so that's f cosine theta. That's fx. Then what we can do is we can plug that equation into there. So we're going to have f cosine theta minus my force of friction equals mass times acceleration in the x direction. Now we simply need to solve for acceleration. Oopsie. So we're going to divide each side by my mass. My masses here will cancel out, and I'll get acceleration in the x direction is going to equal the pull force times the cosine of theta minus my force of friction divided by my mass. Now, this is the answer that they are looking for. And so that's how we could solve for that in terms of the force of friction. Now, what they could say as well is they could say, well, what is the force of friction? And we could say, well, we know that the force of friction is going to equal my coefficient of friction times my normal force in this case. And so we could have to then start plugging things into there for maybe a more complicated question. If we were to do that, then we would say, okay, the sum of the forces in the y direction is simply going to be my normal force plus my y component minus my weight equals my mass times acceleration in the y direction. We would know that the acceleration in the y is going to be 0. And so then we could say my normal force plus my force of y equals my weight. And that can be useful because we might need to know r, right, in terms of that. And so if we simply solve this for r, that would be my weight minus my force in the y. And if we can solve for the force in the x, we should be able to solve for the force in the y. It would essentially be the same thing, but instead of the cosine, we would use the sine for that y side. So we could rewrite r as equal to the weight minus the pull force times the sine of theta. And what we could do then is we could plug that r into that equation and then plug my force of friction into the other equation. And so this is not what is needed, but it is something that could be, right? So this would be my pull force times the cosine of theta minus my, so let's not skip steps with this, minus my coefficient of friction times my normal force divided by my mass. Okay, we're then going to plug this in for R. So we get acceleration in the x equals my pull force times the cosine of theta minus my coefficient of friction times my weight minus pull force times the sine of theta divided by my mass. Okay? And if we were to clean that up a little bit, F cosine theta minus mu times my weight minus mu times my pull force sine theta divided by my mass. And so it's another way that we could solve for that. But again, we're not asked to, and I doubt that you would be asked to in a problem, right? But we need to be able to solve for this without any numbers and just manipulating my variables and being able to identify what's the acceleration going to be based on the frictional force, the pull force, and my mass. This question says, suppose a block of weight 5 newtons is being hung from the ceiling with a piece of rope negligible mass. From the block, a second block also weighs 5 newtons is hung with an identical piece of rope, and a third block is hung from the second one. What is the magnitude of the force of the tension of the rope that connects the first and second block? So if we have our ceiling here, and we're going to hang that object, let's just kind of go one at a time, right? So if we have this, we have a weight here of 5 newtons. It's going to hang there, so we also have to have a tension force up, which is also going to be 5 newtons for the fact that the net force has to be 0. So let's add our second block, right? So we have our first block there. We're going to have our second one here. And if we look at that, then there is the weight here, which is 5 newtons, and the weight here, which is also 5 newtons. And so what would be the force upwards on the top one? It would have to be 10 newtons, right? Because we have 2 5 newtons pulling up on this one. The tension then in the bottom one would simply be 5 newtons, okay? So this force and this force and this force would all be the same, but my 10 newtons would be the largest of the 3 forces. Now, if we keep going, and now we have our third object that is being hung. 1, 2, 3. And our question simply asks, what is the magnitude of the force of tension on the piece of rope that connects the first and second blocks? So we are looking for the tension on our blue rope here. We'll make that one blue. So what are the weights? We have 5 newtons down, we have 5 newtons down, and we have 5 newtons down. In this case, we have the tension here has to be pulling up at 5 newtons. The tension at the top would have to be pulling up at 15 newtons, and the tension here would have to be pulling up at 10 newtons. Okay, and this can get confusing. Like, don't overthink this. Okay, but if we look at simply this second block, so block number 2, there are multiple forces acting on it. One is we have our weight. We also have, we'll call this the green rope, and we'll call this the purple rope. Okay, so we also have the green rope pulling down on block 2, and we have the blue rope pulling up on block 2. So if we work from the bottom, okay, we have 5 newtons weight here, and my green rope must also be pulling up then at 5 newtons. So we know then if the tension in the rope is 5 newtons on one side, it's got to be 5 newtons on the other side as well. Okay, so the tension in the green rope is 5 newtons. We know the weight of the block itself is 5 newtons as well. And the only other force then acting on this second block is the blue rope, and that's pulling up. And the net force has to be 0, so the net tension in that rope then has to be 10 newtons as well. So this question says, a passenger standing in an elevator says that they feel lighter at a certain moment. Which of these could be a reason why they feel lighter? So this is a pretty classic situation in physics where we look at someone that is standing in an elevator. Okay. Now, what we have to think about is if this person is standing on a scale, what is that scale reading? Right? So the person themselves would have two forces acting on them. They would have their weight, or the force of gravity, acting straight down, and they would have the scale pushing up, which would be their normal force. Right? And so whatever the scale reads is going to be what their normal force is. Okay? So if we think about this, there's really three scenarios when the force of gravity equals the normal force, and that's going to be when it's either at rest, and because in that situation, if we did the sum of the forces in the y direction, is simply going to be the normal force minus the force of gravity equals mass times acceleration in the y. So if those two forces equal each other, like we said here, then it's going to be at rest, or it's going to be moving up and down at a constant velocity. Now, there could be an instance where we have the force of gravity which is greater than the normal force. In that case, then, my net force would be pointing downwards. That would be my net force downwards. And so I would be accelerating also in the downward direction, right? In this case, the scale itself is going to be reading less than the person's weight. Okay, so that would be an instance where the person feels lighter, right? The scale is reading a smaller number than the actual weight of the person. The other scenario would be when the force of gravity is going to be less than the normal force. So my normal force is actually going to be greater than the force of gravity. And in that case, if the normal force is bigger, that means the scale would be reading that, or the net force would have to be upwards, and my acceleration would also be upwards. And in that case, the scale would be reading more than the weight of the person, which would mean the person feels heavier, even though they're not actually heavier. They would feel heavier in that instance. Okay? So if we're thinking about all those scenarios, when we want this scenario here of when the person feels lighter. So what could be happening when our acceleration is in the negative direction? Well, one thing that could be happening is we could have the person starting to move down. That would be one instance where the acceleration would be in the downward direction. We'd go from at rest to moving downwards, so we'd have to have an acceleration downwards. Or we could have a situation where the person is moving upwards but slowing down. Right? Both of those instances is going to have a sensation of you feeling lighter. Right? If we're then to look at the other scenario, when we have an acceleration upwards, two instances could produce that, right? And they're kind of opposite of the ones we just stated. Starting to move upwards, or moving downwards, and then you start to slow down. Both of those could produce instances of our normal force greater than our force of gravity. For us, though, the best answer for this one is simply going to be moving up and slowing down based on the choices that are provided. So this question says, which is the correct free body diagram showing the forces acting on an accelerating all-wheel drive car? So I'm not going to show all of the options, but I'm just going to point out the one that is the correct choice for the fact that we need to make sure we understand how to choose forces for an object that is accelerating, right? So if we say that the object is accelerating, that means that the net force is greater than 0. And so if we go through these forces that are on the car, we have these two up forces are going to cancel out with this single down force. And then we have two forces. So this force and this force, I would say, look pretty equal in size. So those would cancel out as well. But then we're left with this force here, which is continuing to push it forward, which would mean that the net force here is not 0. Or, yeah, that it is not 0. There are unbalanced forces, and so this object would accelerate forward. Looking at this problem here, an object with a weight of 25 newtons is hanging from a stationary from two strings, A and B. String A breaks. Calculate the magnitude and direction of the initial acceleration of the object. All the data is given in two sig figs. So first, we're trying to find the magnitude of the initial acceleration, and then what's the angle of that acceleration below the horizontal. So if we look at that, right now we know that the net force before string A breaks is 0. And so the first challenging part of this question is just figuring out what is the value of the net force, because we need to find the value of the magnitude of acceleration. So when A goes away, what must have been left is a net force in this direction at 15 newtons. And that has to make sense, because if this force was keeping it in equilibrium, when we get rid of that force, the new net force then must be 15 newtons in the opposite direction. So we're going to say this is our net force of 15 newtons. And so to solve for acceleration, we simply need F net equals mass times acceleration. I'm going to use this concept of weight equals mass times gravity to get my mass. So my mass is simply going to be my weight divided by my gravity, which is going to be 25 newtons divided by 9.81, which is going to give me a mass of 2.55, and we'll just go 2 sig figs, so 2.6 kilograms. So that's my mass. So now I'm going to find my acceleration. Using this equation, then I'm going to solve for acceleration, which is going to be F net divided by my mass, which is going to be 15 newtons divided by 2.6, which will be 5.8 meters per second squared. The second part of the question asks for what's the angle of the acceleration below the horizontal. So what I'm going to do is I'm going to add my vectors and show us how we can find our angle. So if this is my object, I'm going to have two forces acting on that. One force is acting straight down at 25 newtons. The other force is acting up at an angle of 20 newtons. And we knew that there was a force this way at 15, and that these two forces were perpendicular to each other at a 90-degree angle. So when we add vectors, we actually need to add them head to tail. So I'm going to take this 20 Newton force, I'm going to slide it down here and redraw it here. So I have 20 newtons up at some angle. So there's my 20, 20. And so my net force then is going to be 15 newtons in this direction. Okay, now, based on the idea that these are perpendicular, this angle here should also be perpendicular. So this is an angle here. And what I have is I have a nice triangle here that I can then work with. Okay, and it is a 90-degree triangle. So it asks for what is the angle below the horizontal. So if I draw my horizontal line here, I'm trying to find this angle here. So to do that, I'm going to find this angle here. And then I know that this angle plus this angle here will be 90 degrees. So I can find that angle there. So to do that, I can really use sine, cosine, or tangent. I'm going to use this value as my hypotenuse, and I'm going to use 15 as my adjacent side. So I know that the cosine of theta is going to be adjacent, which is 15 divided by 25. I'm then going to find, divide each side pretty much by cosine. That's pretty much what we're doing. And so I get theta equals the inverse cosine of 15 divided by 25. That is going to give me 53 degrees, which if that's 53, again, that's this angle here. I need this angle here. So 53 plus 37 is going to be 90 degrees. So this then is going to be 37 degrees below the horizontal. All right, this question takes a look at, we have three masses that are hanging over a string and two smooth pulleys, and we're trying to determine the angle the three sig figs made here. So what we have to understand is that everything's in equilibrium, and really our focus is going to be on this middle object here. And if we were to draw the forces here, we would have the weight of the object, or the force of gravity. We'd have a tension force here. We'll call that T right. And then we'll have a tension force here. We'll call that T left, right? And those three forces have to add up in some way to zero based on their angle and their magnitudes, okay? So if we focus on the object on the left, this only has two forces, which would be the force of gravity, and we'll call this T left. And really the tension in this string is going to be consistent. So whatever this value is, it's going to be this value. And so we're just going to use G as equal to 10 in this problem. So the force of gravity in this case would be 4,000 newtons. So then my T left is also 4,000 newtons. Same thing on the right-hand side. This is going to be the force of gravity, which is going to be 5,000 newtons. And then up here, we're going to have T right would also be 5,000 newtons. And that would keep those two objects stationary because their net force would have to be zero. So now if we focus on our middle object, right, we know the values of the forces. We're going to have the force of gravity down at 6,000 newtons. We're going to have a force up at some angle of 5,000 newtons here. Oops. 5,000 newtons here. And we're going to have a force up at some angle of 4,000 newtons here. And the idea is that these T left, right, so this is T right, has T right in an X component, and it has a T right in the Y component. Same thing over here. T left in the X component and T left, excuse me, in the Y component. And so if we were to draw our net force equations, right, in the Y direction, we have T left in the Y plus T right in the Y minus the force of gravity equals mass times acceleration in the Y. And again, that equals zero. And in the X direction, we have tension left in the X minus tension right in the X equals mass times acceleration in the X, and that equals zero. So it doesn't really matter which way we say is the positive or negative. We just know that these two forces in the X and Y direction are going to cancel each other out. Now, if we look at this, actually getting through this, I don't really like this question for the one fact that it's going to require us to do the law of cosines. But what we can look at is if we look at these forces, right? So we have 600 newtons down. We have 500 newtons up at an angle. Or 5,000, sorry. So all these are 5,000, 6,000. And then we have 4,000 newtons up here, right? And so all these forces added together have to equal zero. So their triangle that they produce has to end back where it started, right? So if I start here, I have to end there. And so what you could do is you could then use the law of cosine to determine that. I'm really not one to want to worry about that, okay? So we're just going to say that angle is 97.2 degrees. Typically what we'll have, though, is just a simple understanding of how these forces all have to interact. So I'm not worried about how to use the law of cosines. We can use that in math class, but for us, let's not worry about that, and let's just know that this should be our correct answer. So this question says 3 wooden blocks are placed on a smooth horizontal surface. A push force is applied to the 2 kilogram mass. The blocks accelerate to the right at 2 meters per second squared. Determine the size of the force F in newtons of the 1 kilogram mass acting on the 2 kilogram mass. So the idea that this 1 kilogram mass is pushing backwards on this 2 kilogram box there. Well, what we have to understand is that that 2 kilogram mass is also applying a force this way, and these two forces are going to be the same even though their arrows are much different, because if the 1 kilogram mass is pushing backwards, the 2 kilogram mass is pushing forward. And that 2 kilogram mass is going to push both the 1 and the 3 kilogram mass forward with the same acceleration. So we can say that F is going to equal mass of 1 and 3 times acceleration. And Newton's third law says if that's true, whatever force the 2 kilogram mass is pushing forward, these two masses are pushing backward on this 2 kilogram mass. So let's do that. So F then is going to equal the mass of 1 plus the mass of 3, because that's the total mass that we're accelerating forward, times an acceleration of 2. So that's going to be 1, whoopsie. It's going to be 1 plus 3 multiplied by 2. So that's 4 times 2, which is simply going to be 8 newtons. So the mass is pushing back with the same force of 8 newtons. And now we could, and it's not asking us to, but we could solve for this push force, right? Because if we drew our 2 kilogram mass here, here are the forces that are acting. We have the weight, or the force of gravity. We have the normal force. Those two are going to cancel out and really not a factor in this problem. And then we have our push force. So we'll call that F push. And then we have our resistive force, and we know that's 8 newtons. And we have a mass here of 2. And so the sum of the forces that are acting here in the x direction are my push force minus F equals mass times acceleration in that direction. So we're going to solve for F push minus 8 newtons equals my mass, which is 2 kilograms, times my acceleration, which is still 2. So that's going to be 4 newtons. We're going to add 8 newtons on both sides, plus 8 newtons. So my push force, in this case, would be 12 newtons. And that would be a way that I could push that object forward. Now, the last thing is this should make sense for accelerating all of it, right? If we think about all of the objects, right? If we have a push force of 12 newtons, right? So we'll say F push equals the mass total times the acceleration. So this is 12 equals my total mass, which is 6, times my acceleration, which is 2. And that all comes out nice. So this question says, a wooden block of mass 2.8 kilograms is sliding down a slope with an acceleration of 0.36 meters per second squared. Slope makes an angle of 16 degrees with the horizontal. Calculate the coefficient of dynamic friction. So this is a ramp problem. So let's draw our ramp. And it's going to make an angle, like it said, of 16 degrees. So this here is going to be 16 degrees. Now, if we draw our object here, it is going to have the forces of gravity acting straight down. The normal force is going to act perpendicular to my ramp, and it is accelerating down the ramp, right? So it's moving downwards. So the frictional force is going to be up the ramp. And we're going to say that the direction of the x and y axis is again tilted. So our positive x direction is going to be down the ramp, and then our positive y direction is going to be perpendicular up the ramp. So what we need to do is we need to break our force of gravity into its two components. So we're going to break it into its perpendicular component, and we're going to break it into its parallel components. And this angle right here is going to be equal to my angle there. So the angle that is produced from this triangle is the same as the angle that the ramp is going to have as well. So let's set up our net force equations. Sum of the forces in the x direction is simply going to be the parallel component of gravity minus my force of friction equals mass times acceleration in the x direction. The sum of the forces in the y direction would be my perpendicular component of gravity minus, my normal force minus my perpendicular component of gravity equals mass times acceleration in the y. Now, we know the acceleration in the y is going to be 0, and so my normal force is going to equal my perpendicular force. And we can solve for that by saying perpendicular is the cosine of theta equals my angle perpendicular divided by my force of gravity. So my perpendicular force is going to be my force of gravity times the cosine of theta, which force of gravity is mass times little g times the cosine of theta. So that's how I would solve for my perpendicular force. Now, the question asks for the coefficient of friction. And if we look, this is where that is going to be found, because we know that the frictional force for something that is sliding is going to equal the coefficient of dynamic friction times my reaction force, which in this case is going to be my normal force, which is also my force perpendicular. So we're going to take those things and plug them in to there. Okay, but things that we also know. We know the acceleration. That's right here. We know the mass here. And we can also solve for our parallel component of gravity. So I'm going to take this equation and we're going to put it back down here. So my parallel component minus my force of friction equals mass times acceleration in the x direction. If we plug in what we know, if my perpendicular component is mg cosine theta, my parallel component is going to be mg sine theta. It's the opposite side. So we're going to have mg sine theta minus my coefficient of dynamic friction, which is what we're solving for, times my reaction force, which, again, we said my reaction force is going to be my perpendicular force, which we solved for that here. So I'm going to put mg cosine theta here equals mass times acceleration in the x. So, again, we wrote the frictional force as the coefficient of friction times my reaction force, and my reaction force is my perpendicular force here. So, some things that are nice. One thing is that m is in everything, so the mass actually goes away. And then all we have to do now is do a little bit of algebra to solve for my coefficient of friction. So to do that, I'm just going to rewrite this. So it'd be g sine theta minus mu d g cosine theta, g cosine theta equals acceleration in the x. I'm going to add a mu d g cosine theta to each side. And in doing so, I'd get g sine theta equals ax plus mu d g cosine theta. Now, there are faster algebraic ways to get this, but I'm just showing you kind of the long way so we can understand what we need to do. Each side I'm going to subtract ax, and I would get g sine theta minus acceleration in the x equals coefficient of dynamic friction, g cosine theta. So then the only thing that's left is I need to divide each side by g cosine theta. So I get my coefficient of dynamic friction is going to equal g sine theta minus acceleration in the x divided by g cosine theta. I'm going to plug my values in my calculator, and I'll be able to get my answer. So when I do that, I get coefficient of friction equals 9.81 times the sine of 16 minus 0.36, I believe it was, 0.36. That's the acceleration down the ramp, divided by 9.81 times the cosine of 16. And all that gives me 0.249, 0.249. Again, that is a unitless value. Basically, it tells me I need to push with roughly about 25% of the weight to overcome the impacts of friction. So this question says, a wooden block of weight 10 newtons is moved along the surface at a constant speed of 2 meters per second by a constant horizontal force of 5 newtons. Which of the following is the correct statement about the coefficient of static friction between the block and the surface? So let's just do this, right? The other forces that we would have here is we'd have our normal force right there. And with that then, because it's a constant velocity, we know that there must also be some frictional force basically acting opposite of my push. So the net force in the x direction is going to be my force push minus my force of friction equals mass times acceleration in the x. Now my acceleration is going to be 0 because it's moving at a constant speed. So I am not accelerating. Now this question can be tricky because it's asking for static friction. And static friction is occurring before the object is actually moving. So let's just think about if this is as big of a force as I'm going to be able to push on it, like my force of friction maximum of static is only going to be 5 newtons. So if we were to take the equation for the force of friction for something that is static, that has to be greater than, or excuse me, it's not greater than, but it's less than or equal to the coefficient of static times the reaction force, which in this case, my reaction force is my normal force. And my normal force is going to equal my force of gravity because those two forces are going to cancel out. So the force of friction maximum is going to be less than or equal to my coefficient of friction times 10. And if my frictional force, the maximum value is 5 based on how hard of a push I can apply. So that means then that my coefficient of static friction, right, if we were to just solve this out, whoops, there's the answer down there, but if we were to just solve this out, the coefficient of friction is going to equal 5 divided by 10. So that means 0.5. So what that tells me is that it cannot be greater than 0.5, right? 0.5 is really the maximum that it can be, because if it is greater than 0.5, then this force of 5 newtons isn't going to be able to push this block from rest. Now, if I'm only applying a 5 Newton force, the maximum coefficient of friction can be is 0.5. So if we look at this question, it says an object is dropped from the top of a tall building. How does the air resistance on the object vary with time? And our answer is that it increases and then stays constant. Now, if we think about that, if this is our tall building, okay, as our object is falling off of it, initially we just have the force of gravity that's acting on it, or the object's weight. There is some drag, but it's very insignificant. Now, as that object falls farther, because it's moving faster, it's going to start to get some air resistance that's going to reduce the acceleration. However, the net force in this situation is still down, so it's still going to accelerate downwards and still speed up. Still here, the force of gravity, we point it down, but because now it is moving faster, my air resistance will increase to the point where it's going to equal my force of gravity. Okay, air resistance is dependent upon a few different things. It's dependent upon the velocity squared, it's dependent upon the density of the liquid or the fluid that it's traveling through, and it's dependent upon the area of what is exposed to the air. So in this situation, density doesn't really change, area doesn't really change, but as it increases its velocity, the air resistance will increase. Once it gets to a point, though, where my air resistance equals my force of gravity, the velocity would be constant, and so my air resistance would stop increasing and just maintain a constant force as well. This question says, an empty minecart has a mass of 10 kilograms, can be filled with coal, and which can be transported a horizontal shaft track. The effective coefficient of dynamic friction between the cart and the track is 0.6. If a stationary cart is filled with 100 kilograms of coal, which of the following forces will move the cart with the lowest non-zero acceleration? So if this is our cart moving along the track, and we're going to fill it with coal, we're going to have a total mass equal to 110 kilograms. So our force of gravity would be down. We would have our normal force up. We would have a frictional force. And basically, we would have some push force acting. And we want to know what is the which force will move the cart with the lowest non-zero acceleration. So which force is going to do that? So basically what we need to do is we need to figure out what's our force of friction in this scenario. So that's going to be coefficient of dynamic friction times my reaction force, which is my normal force. That's going to be 0.6 times 1,100 newtons. And if I get that, that's going to be 660 newtons. So that's my frictional force maximum. And so any force that I'm going to be able to push it with a non-zero acceleration is going to have to be greater. So F push is going to have to be greater than 660 newtons. If it's not, if it's less than that, it's not going to accelerate forwards. It's going to accelerate backwards and actually slow down. If it's equal to that, it's just going to move at a constant velocity. So I need to find an answer that is greater than 660 newtons based on the answers provided. Our next question says, a potato of mass 0.15 kilograms is dropped from a tall building, reaches terminal velocity. What is the magnitude of air resistance at that time? Give your answer to 3 sig figs. So if we look at this, our answer is going to be 1.47. The concept is if this is our tall building, and we have our potato that's thrown off of our building, there are going to be two forces that are acting on it when it reaches terminal velocity. Our force of gravity and our air resistance. Those two forces have to be the same based on the idea that the sum of the forces in the y direction must be 0 as long as it has reached terminal velocity. So what we need to do is solve for my force of gravity, which is mass times g, which is 0.15 times 9.81. Whatever that value is going to be, it's going to equal my air resistance, and that's going to give us a value of 1.47 when answered with 3 sig figs. All right, so looking at this question, it says a post is kept vertical stationary by 3 chains attached in tension to the top. 2 of the 3 chains are shown. The tension in the 2 chains shown is the same. At what angle clockwise from the dashed line must the 3rd chain be fixed? Round your answer to the nearest degree. So if we look at this, I'm just going to imagine each chain currently attached has a tension of 100 newtons. And then what we're going to do is we're going to find currently what is the net force in the x and y direction just with those 2 chains, because if it's at rest and kept stationary as said here, then my 3rd chain is basically going to have to balance out whatever the net force is of these 2 chains. So we're going to break this chain on the right into its x component and into its y component. So the sum of the forces, and then we'll just say that to the right and up is in the positive direction. Okay, so in the x direction, we have the x component of the force minus 100 newtons, and we'll find out what that is. In the y direction, we simply have the y component of my force. So if I look at this triangle here, this is my adjacent side, this is my opposite side, and we know the hypotenuse is going to be 100. So if we do cosine theta is going to be adjacent, which is going to be my x over my hypotenuse, which is 100. So my x component is simply going to be 100 times the cosine of 35 degrees. When I plug that in, I'm going to get 82 degrees, or 82 newtons, excuse me. So this is going to be 82 minus 100 equals negative 18 newtons. In the y direction, we're just simply going to have the same setup, but instead of cosine, we'll use sine. And I should get a value of 57 newtons. And that should make sense, right? If this is 35 degrees, my x component should be bigger than my y component. So 57 and 82 makes sense there. So my net force currently with only 2 is 57 newtons in the y direction and negative 18 newtons in the x direction. So we need our third chain to produce forces that are opposite of those. So in the x direction, we're going to have 18 newtons this way, and in the y direction, we're going to have negative 57 that way. And so the net force for my third chain would point in this direction. And we don't actually need to find that. All we're simply trying to find is the angle. And the angle would be this angle created right there. So that's my theta. So if I know the x components and the y components, I don't need to find my total component. I can simply use the concept of tangent. And that tangent theta is going to be my opposite, which is 57, divided by my adjacent, which is 18. So then my angle is the inverse tangent of 57 divided by 18. When I plug that in, then I get an angle of 72 degrees. So that's the value of how the angle I'm going to have to apply a force here. It is not going to be 100 newtons, but it is going to have components of 18 and 57 there. This question here says a person stands on a set of scales in a stationary lift elevator and records their weight as m. When the lift accelerates downwards, what will happen to the reading of the scales? So the main idea with this is for something to accelerate downwards, the net force must also be downwards. And so if we think about an object that is simply standing on a scale, the two forces acting on them is the force of gravity, or their weight, and then the normal force. And the normal force is the scale pushing up on them, which is what the scale actually reads. So if our net force must be downwards, these two forces can't be in balance, and that the normal force must be less than the force of gravity. So what will happen to the reading on the scale is that it would go down. If the scale value goes down, they would feel weightless, or they would feel less heavy. If this was accelerating upwards, then the normal force would have to be greater than my force of gravity, and the scale would read a greater value than their actual weight.